Well, hey, it's Dr. J. Today we're going to learn the chain rule. One of the most important of all the rules and necessary as we move forward to resolve some issues with taking derivatives of more complicated functions that we refer to as chains. So a chain in mathematics is formed by a composition. So something like f of g of x. Okay. An example would be something like f of x is x to the 99th power, and g is 3x squared plus 5. Then the composition f of g of x is equal to, well, we take the formula for f, which is x to the 99th. You can think of the parentheses as being x. Yeah. We remove the variable x, and we put g inside where the x used to be. And so this would be 3x squared plus 5 to the 99th power. So this would be called a chain composed of f and g. So that's what we mean when we say a chain. Throughout this video, you'll hear me use the terms inner and outer. So f of x is called the outer function, and g of x is called the inner function. Sometimes I'll say inside, outside, or inner and outer throughout this video. Now, if this were an algebra class, you'd be done. That would be the answer. Perhaps I would have you plug in a value for x and evaluate some output for this composition. And we might do several different versions. We might go one direction or the other and what have you in an algebra setting. But this is a calculus course. So in a calculus course, the question is, how do we take the derivative of a chain? Okay, so let's call this example 1. Let's find the derivative of the chain 3x squared plus 5 to the 99th power. How would I do that? Well, it would be very difficult. Yeah, it would be very, very difficult. I'm going to give myself some more room because that's how difficult it's going to be. In order to take the derivative of 3x squared plus 5 to the 99th power, I would have to write this out as 3x squared plus 5 times 3x squared plus 5 dot dot dot. That means I'm too lazy to write them all out. And all together, there would be 99 factors, or what we say 99 times. It's one of the reasons why we call them times or times tables, or we say 5 times 3 or 6 times 8. It's because that's how many times, or that's how many occurrences there are of that factor. Okay. That would suck. Even for somebody like me who loves math, I dream math, and this would be a nightmare to me. Although if I was trying to fall asleep, it might be better than counting sheep. You could sit there and think about all 99, count them down, 99, 98. It'd be like, playing 99 bottles of math on the wall. Okay, so how are we going to do this? Well, what we're going to do today is we're going to develop a rule to make this a lot easier. Now, I could just tell you the rule right now, but you know me. You've been watching these videos for 7 or 8 weeks now, or however long it's been, 6 or 7 weeks. Where are we? We're almost halfway through. And so you know I never do anything the easy way, right? I'm not just going to tell you the answer. I'm going to dig it out of you, or I'm going to make you watch me dig it out of here, all right? So what we're going to do is to develop a rule. We want to look for a pattern. You know, in math, we don't just make up rules for the sake of making rules. We don't, we're not like, enforcers of rules just for the sake of a rule. A rule is really a property. That's what a rule is, right? It's a rule in the sense that it defines a process. And in order to define a process, we need to have a pattern. We need to be able to recognize that when this happens, we can predict. That's what patterns help us do. Predict the result. If we can predict the result, then we can develop a rule. All right? And so that's how we do it in mathematics. We don't just say, oh, this is a rule, just because we like making rules. So how do we do this? We're first going to take the derivative of just 2 factors. Right, so 99 is way too many, so we're not going to try to do 99. We're just going to try 2 and see what happens and look for a pattern. All right, let's do 2. Ready? This will be easy. This is just the product rule from the last video, or from a couple videos ago. It's a nice review of the product rule that you hopefully remember from the last couple videos. So 3x squared plus 5 squared means to write 3x squared plus 5 twice. So it's going to be the first function times the derivative of the second function derivative of the second function is 6x plus the second function, which, by the way, the second function and the first function are the same, so that's why these are twins, times the derivative of the first function. So because these are 2 factors that are identical, when you do the product rule, you're going to get 2 copies of the same thing. So there is an invisible 1 right here and right here. Invisible. So what we're going to do is add these together. And I'm going to leave it unsimplified. When you're looking for a pattern, it's nice to see the inside of every function, sort of what it's composed of. It's like in science, when you dissect something and you look at its internal organs, right? You can see everything is connected to everything else, and you can make, scientific observations. Well, in math, we don't cut open frogs or, pigs' eyeballs or anything like that. What we do is we dissect functions. Yeah. These are our creatures these are the poor things that we're cutting up and piecing them back together in different arrangements. All right, so we're going to leave that unsimplified. That's a result for a second power. Let's try it again for a third power. And we'll do this as many times as it takes until we see a pattern. Typically, the minimum is twice before you see a pattern. So this is going to be the derivative. Now, let's make an observation. A third power, instead of writing it 3 times, I'm going to write it squared. So this represents the first 2 times the third one. There's a couple of reasons why I'm doing this. One is obvious. My board is not big enough to write it all 3 times. Although I probably could have made it fit. But there's another reason. I already know the answer to this one. Yeah, 3x squared plus 5 squared. I already have it. Yeah. So it's going to be the first 3x squared plus 5 squared times the derivative of the second, 6x, plus the second times the derivative of the first. But the derivative of the first, I already know it. It's right here. I'm running out of space. Sorry. I just had to scoot over a little bit to make myself some room. So I've got the first times the derivative of the second plus the second times the derivative of the first. But the derivative of the first, I already know. And I'm going to do this in every one of these steps. Already done. Yeah. So if something has already been differentiated, I've already found the derivative, I don't need to do all this work again. I can just copy that work in my next step. All right. So now we have 3x squared plus 5 squared times 6x plus this 2, I'm going to move it to the front. Not all the way to the front, but just to the front of this group here. And then I'm going to combine, this is 3x squared plus 5 to the 1, and then another 3x squared plus 5 to the 1. And that's going to be 3x squared plus 5 to the second. And what do you know? Another copy of the same factor. Remember the invisible 1. There's an invisible 1 right there. So when I add these 2 together, I got a 1 plus a 2. These are identical. They're the same exact factors. So I have 1 of these factors plus 2 of these factors. So I have 3 of these factors. Shush! The dogs are barking. Come on. Come back here. Back here. Sorry about that. My dogs are watching me do my math lectures today, and they're barking at the mailman. How cliche. All right, so that's the answer to the third power. So we're looking for a pattern. Let me erase some of this messy work here and just write the results. Sometimes when you're looking for a pattern, you want to clean up the mess you made and write down a list of results and hope that the pattern appears to you. If the pattern doesn't appear, then you can always do it again and again and again and again. So that's the first one I did, which is a second power. And then I just did the third power. down here is my answer for the third power. And if you don't see the pattern, we could do it one more time. To try to keep this video from being, 2 hours long, I will just show you the result of the next one. The steps are exactly the same as what I just did. I would just, instead of doing it to the third, the next one in the sequence would be the fourth power. I hope you can see a pattern already. 2, see 2, 3, 3. So this is 4, so that's going to be 4. Yeah. Oh, shoot. I wrote something down wrong. It's not a deadly error. It's just slight error that almost cost me when I was looking for my pattern. So the first one has a first power. This one has a second power. So the one I'm about to do must have a third power. And then notice the 6x just kind of goes along with the rest of them. Do you see the pattern? Let's do one more. I can almost hear you screaming through the internet. I see it, Dr. Jordan. I see it. I see it. This is going to be 5 squared plus 5 to the 4 times 6x. So in general, if this was 99th power, I don't actually have to multiply it 99 times. I can just follow this pattern or the rule. It's going to be 99. 3x squared plus 5 to the 98th, and then times 6x. So this is the answer to example 1. I erased example 1 a long time ago, but that's what the question I was trying to resolve. And so this is going to give us our quotient rule. So look at how the rule worked. F of g of x. So did I say quotient rule? I'm still thinking about the last example, the last lecture. This is going to give us our chain rule. Still having memories, flashes of the past of when we did the quotient rule, which we might revisit today. I think we will revisit it at some point. So this is called the chain rule. And so you can clearly see what's happening here, right? This is essentially the derivative. So you have g of x to the nth power. And so we took the derivative by using the power rule. That gave us n, then g of x to the n minus 1. That's this. You see the pattern here? It's whatever the power was multiplied in the front and then subtract 1 times the derivative of g of x, right? Where g of x was the inside here, 3x squared plus 5. So that's kind of how the rule plays itself out. So let's formalize that with a new rule. The derivative of a chain, also known as a composition, is the derivative of the outer function, ignoring the inner function, g. That's kind of what we did here. Right? We ignore the 3x squared plus 5. You just carried it down to the next step. Times, and then this little thing off to the side, I sometimes call that the sidecar, sort of riding on the side of the motorcycle, g prime of x. So this is the rule that will win the day for this lecture, called the chain rule. We start very simple with chains that are only composed of two functions, f and g. So let's try another one. Let's find the derivative of five x squared plus 9x minus 4 to the 8th power. Okay. Now, it's still kind of early in the lecture, so I'm going to sort of do a little sidebar here. The sidebar is really just to keep track of who everybody is. So g of x is the inner function. That's a 5x squared plus 9x minus 4. And f of x is x to the 8th. So g prime of x is 10x plus 9. Again, doing that very quickly from the previous lessons. You just multiply the power times 5. So 2 times 5 is 10. And then subtract 1. So that's going to be x. And then this one is a linear function, 9x, or a linear term. The derivative of 9x is just 9. Now the derivative of f of blank is 8 blank to the 7th. And remember, g is inside of f. I'm writing it very small. Probably going to need more room than that. So g is all of this, 5x squared plus 9x minus 4. All right. I wrote it really tiny here. Don't worry. This is just my scratch or my thoughts. All right. I'm actually going to do the work over here. So we're going to take the derivative. First, we bring the 8 down to the front. Then we subtract 1 and get 7. Be sure that the very first time you use the rule, you don't touch the inside right away. So you're just kind of glossing over the inside. That's your G. Yeah. I wrote it very tiny here, but I wrote it much larger here. All right. And then multiply by G prime. G prime is typically very easy. It's 10x plus 9. And just to be safe, I'm going to use an extra set of parentheses. If I have parentheses, I usually don't use a dot. So I would write the answer like this. There you go. So that's the chain rule. Got about 8 more of these. So it's a very singular lesson. We're focusing on one thing today. Once we got this down, you've practiced this repeatedly, then this will be, you can add this to all the other rules that we've learned about taking derivatives. So I'm going to kind of go through one of each type. I'm also going to revisit all the different notations. So by one of each type, I did polynomials, power functions. Now we're doing square roots, and we'll kind of just go through the whole catalog of commonly used functions in this course. Also, the different notations. So you can have, the previous one was called operator notation or expressional notation. There's no Y in the last one. This one now has a Y. It doesn't really change how you do the problem. It's just when you write it down, it's now written as a function of Y. Or Y is written as a function of X. I should be very careful. With square roots, I recommend rewriting them as 1/2 powers. Like that. Okay, and then now let's do the rule. So the first pass, you take the power, you bring it down to the front. You don't do anything to the inside. The inner function stays the same. Subtract 1 from the power, you get -1/2. And then multiply by the derivative of the inside, 18x plus 8. I'm going to simplify this one a little bit. This is technically the answer. I'm going to do a little bit of simplifying. I'm going to write this as a square root in the denominator. Right? Remember, 1/2 means square root, and the negative means it's in the denominator. I'm going to put the 1 here. And then I'm going to put the 2 over here. So I'm sort of splitting up the 1/2. I'm putting the 1 there, and I'm putting the 2 way over here. And you'll see why in a minute. I'm going to divide both of these terms by 8. I only do this if these terms are both even. If those terms were not even, then I would have just left the 2 right out here in front. But whenever possible, I like to divide to make my final answer a little easier. So I've got 1 over the square root of 9x squared plus 8x plus 3 times 9x plus 4. Yeah, I'm dividing both of these terms by 2. Technically, there's parentheses around this. So I'm multiplying 1 times that. So the multiplication dot goes up in the numerator. So it's just going to be 9x plus 4 over the square root of 9x squared plus 8x plus 3. That's as good as it gets. That's the final answer. I'm going to play around with various levels of simplification today. Sometimes I will simplify it a lot. Sometimes I will simplify it a little bit. And sometimes I won't simplify it at all. Right. On your end, as a student, I want you to practice all 3 of those things. Sometimes I'm very clear about how much simplifying I want. Sometimes I'm not. Sometimes I just say simplify. Generally, if you just see the word simplify, that means do the best you can. You should always read into it as much as possible, or as much as you possibly can. Right? And everybody will experience different numbers and different obstacles along the way that might trip you up, but that's it's an experience, right? We're not here just to get a grade. You're here to get an experience. That's what this is all about. And I'm trying to really show you a little bit of everything. Let's do another chain rule. How about this one? This one doesn't have a y. This is a derivative of, sorry, it's not an x either. It's a t. 6 minus 10 t squared. This one doesn't have an x or a y. This is a derivative with respect to t. When we get back to talking about business math, t is time. We talked about that early in the semester. We're talking about loans or investments. Time can be measured in days, weeks, months, years. It can even be measured in minutes and seconds and things like that. You know that. We've done some problems with time. Sometimes I'll do a problem in X and then I'll switch to T. Sometimes I will write T, but I will treat it exactly like an X. That's the most common thing. If I was drawing a graph, I would draw T just as if it were X. It would be the horizontal axis. So keep that in mind when you're doing math. The letter that you use really doesn't change the result. This one's actually rather quick. I could probably finish the whole problem in one stroke here, maybe one or two strokes here. Remember, a little memory recall here. The derivative with respect to x is just of e to the x is just e to the x. All right. So that means the derivative with respect to t is just e to the whatever this is. It's 6 minus 10t squared. That's it, right? Now then you have to apply the chain rule. Right? So this is the first link in the chain times the derivative of the other function, or the inner function, which will be negative 20t. Right? The derivative of 6 is 0. The derivative of negative t squared is negative 20t. Now this looks terrible. Multiplying by a negative. So I'm going to rewrite the negative in the front, then the 20t, then the e, and then the power 6 minus 10t squared. So that is your simplified answer. Two of my favorite functions are the natural exponential and the natural log. So the natural exponential is base e, and the natural log is the log base e. So this is the logarithm of a function that is based e. So these are very much related to each other. Although these two questions aren't directly related to each other, the two functions live in the same, or are part of the same family of functions. So now I'm using this function notation. I switched back to my favorite, most common variable, which is x, and I want to find the derivative. Find the derivative, f prime of x. Okay, let's do another little memory recall here. Keeping my brain cloud open here. The derivative of ln of x is 1 over x. The derivative of ln of x is 1 over x. Now, if this were a different type of logarithm, it would be a little more complicated. But for natural log, it is very simple. Derivative of ln is 1 over x. Now, this is a chain rule, so it's the derivative of the ln of g. So this is like your g function. It's inside of f. Is going to be 1 over whatever that is. The whole enchilada. So in other words, all of this is like x. So here's the way I write it. ln of blank is 1 over blank. And then if you're using a composition, this is a function g. It's not necessarily x. All of this is g. All right, we call the inside g, or g of x, same thing. Or in this case, g of t, yeah, because the variable is t. So now I have to do g prime. Yeah, g prime. All right, now I'm going to have to take back that space. This is what I'm going to write here, which is g prime, but if I had more space, I would write it in another line, but I'm not going to. I'm going to go ahead and do it right here. Take the derivative. It's going to be 12x squared minus 16x plus 7. And be careful, that does not go on the denominator. It goes up in the numerator. So sometimes it's nice to move this dot up here. So when you're multiplying 1 times, then this function here goes on top. So my final answer, I can remove all the parentheses. 12x squared minus 16x plus 7 all over 4x cubed minus 8x squared plus 7x plus 2. And there's my answer. Okay, not too bad. So some functions are going to be much easier to differentiate than others. Yeah. All right, let's keep moving. We're halfway done. So now we're going to combine all the rules that we've learned in this last week or so. The chain rule combined with the product and the quotient rule. So let's do product rule first. The most common name for a function is f. I pointed out earlier in the semester that when you call a function f, it doesn't mean that it's forever f. You know, you could have a function called f and then, you know, another function called g, and then later on in the problem you might rename them or relabel them. Oh, I forgot one of my letters here. That's a 7 right there. So this function is called f, but in the chain rule, the inside and the outside are called f and g. So it can be a little bit confusing. And you have the product rule, which also uses the letters f and g. So it's like, will the real f, you know, please stand up, right? Who is the real f? Well, it turns out it doesn't matter. You could call this function f. F just means function. Yeah? You could call this function f. You could call the whole thing f. You could call the first part f and the second part g. You could even use different letters, J and K, A and B. U and V are pretty common. We use like U and V for two different parts of a function. So what you call them is not nearly as important as how you manage them. So this is going to first be a product, right? Identify that there is a product separating these two. Then a chain. So a product followed by a chain. So let's first handle the product. Product rule first. All right. So we've got the derivative of the first function times the second function plus the derivative of the second function times the first function. Lots of parentheses here. So that's the product rule. All right. If you like the other letters, it's A and B. So it's A prime B plus B prime A. Yeah. Or U prime V plus V prime U. Or in the original form, F's and G's, F prime G plus G prime F. But again, that's confusing because this is already called F. So it's like there's two F's. Next, you do the chain rule. So the chain rule. The derivative of the first piece, that's going to be 5, 8x squared minus 6 to the fourth times 16x. So that's the chain rule. Going right back to example 1. Now I'm going to get rid of these extra brackets here. 4x squared plus 9 to the 7th. I was using these extra bracket parentheses to keep these separate from each other. Now they're all combined together. All right, and then now the derivative of the second function. 7, 4x squared plus 9, 8x. Yeah, again, chain rule again. Oh, and I almost forgot. Subtract 1 from the 7, so that becomes 6. Now I want to check all of them. Yep, okay, good. And then the last function, I can remove the dot and remove the extra brackets. And there you go. You may leave this answer unsimplified. Now, if you really want to go a little further, here's the now I probably shouldn't be saying this. It's just going to make it drag on longer, but I am a little obsessive and compulsive, right? I suffer from that. I've lived with it my whole life, but in some cases it actually benefits me, and it might benefit you too, right? Especially in the next chapter. So for today's lesson, you can stop right here and fast forward what I'm about to say. But if you want to, go the extra step, don't go too far though. You got to know when to quit. The only things that I would do personally as a seasoned mathematician, I would combine these guys, the 5 and the 16, and I would also combine the 7 and the 8. A couple of reasons. Constants like to go to the front. Yeah. Also, this x and this x, they don't have any exponents. They don't have any pluses or minuses. They really want to be out in front. And I'm going to make you do this eventually in chapter 3 anyway. So this is all I would do, though. I wouldn't do anything more than this. I definitely wouldn't try to combine the rest of the terms. So I would do 16 times 5 and make that 80x. And then I do 7 times 9, 56x. That is all I would do. I would probably write them in the same order as well, just because I'm like that. I like things to be neat and orderly. So I will accept either one of these answers. I will caution you not to try to go any further because it'll probably be wrong. Um, until we get to chapter 3, I'll teach you another step. And I'll also talk more about the graphs. We're really going to dive deep into graphing in the next chapter. We've barely scratched the surface of graphing in this chapter. Okay, so that's it for example 6. Let's do the same problem, but with a quotient. Well, not exactly the same. I don't want to be that repetitive, but let's do a very similar problem, but with a quotient. So f of x is a quotient to the 6th power 2x minus 4 over 3x plus 5. All right. First thing I would do is rewrite it like this. 3x plus 5 to the 6th and 2x minus 4 to the 6th. Just so that you can clearly see that they are separate. Having second thoughts about that. So let me just slow down a little bit. I'm really trying to get through this. It's hard to slow down sometimes. This is if you're going to use the quotient rule. So let's call that option B. All right. I thought about it. I just gave it, a second of thought as soon as I said it. Sometimes I say something and then I think about it. I'm like, wait a minute, I should have thought about that before I said it. Option A is to use the chain rule first. You are going to use both rules, right? And it doesn't really matter what order you do them in. In the last one, I didn't really have a choice because the powers were different. These have the same power, right? They're both going to be 6. So I have a choice. As soon as I said this, I'm vetoing this. I'm vetoing option B. It's my problem. I can decide how I want to do it. If I want you to experience what option B is like, I don't know if I'll have time to do it in this video, but if it shows up later, maybe I'll say, hey, remember that one time where I vetoed it and said I didn't want to do it that way? Well, this time I'm going to go ahead and do it that way and see what happens. Right? It might come back. Not today, though. I'm already 48 minutes into this video, which I really wanted to get done in an hour. I don't know if I'm going to meet that goal or not. So we're going to do the chain rule first. So we're going to take the 6 and pull it out to the front. Subtract 1 from the power, so that's going to become 5. And then multiply by the derivative of the inside. Now use the quotient rule. It turns out the two answers would have came out the same, but I'm going to do it this way to get it done. So quotient rule, quick refresher of the quotient rule. You take the derivative of the top, which is going to be 3. Yeah, because that's a linear. We're not looking at the exponent. We're just looking at this thing here. 3x plus 5, 2x minus 4. So derivative of the top is 3 times the bottom, 2x minus 4. Minus the derivative of the bottom, which is 2, times the top, 3x plus 5. All over the bottom squared. So this is your unsimplified answer. Let's do a little cleanup. Now I'm going to write this as 3x plus 5 to the 5th over 2x minus 4 to the 5th times 2x minus 4 to the 2nd. So I'm going to combine those in my last step. I'm going to distribute 6x minus 12 negative 6x minus 10. I'm going to cancel the 6x's. I'm going to add the negative 12 and the negative 10. It's going to be negative 22. And then I'm going to multiply. So first I add negative 12 and negative 10. And then I multiply because I've got this dot here. So it's 6 times negative 22. And I'm going to put that right out here in front. Negative 132. Yeah. And the x's, 6 x's have canceled now. Then I'm going to put my 3x plus 5 to the 5th power. And finally, I'm going to combine the bottoms. Now be careful. Remember the rules of exponents. That's a 5th. That's a 2nd. You're going to add those powers together. 2x minus 4 to the 7th power. And that's your final answer. If I had more time, I would have done it using option B, which is what I originally said I was going to do. But as soon as I wrote it down, I realized that's not the way to go. Although it would have been fun. It would have been a trip, adventure. I encourage you all to try, alternate routes in math, in life. They don't all have to be, strenuous. Just take a different road. Travel the road less traveled. That sounds funny. Take the road less traveled. So that's it for the chain rule of two functions. At least that's it for now. Of course, just like anything, there's always going to be a continuation of this. Once you learn a rule, now you're sort of obligated to keep doing it, right? What happens if there's 3 or 4 or 5? For today, let's just do 3. A chain of 3 functions. Sometimes called a triple composition. Triple composition. F of G of H. And I want to take the derivative of this thing. Well, it's not that complicated because once we have the theory, and once we have the rule, it's not really a theory. This is a practice now. We're not just imagining that we're doing this. We're actually doing it. Right? So we have a theorem, which if you read it in the book, the chain rule is called a theorem. It's very important when you call something a theorem. It's a theory that's been proven and put into practice. We call that a theorem. I'm just calling it a rule, right? The chain rule. I'm adding it to the list of rules. If you're keeping track, I think we're up to about, 7, 8, 9, 10. That's our 10th rule. We started with 7. That was the basic 7. And then we did 8 and 9, which was products and quotients. And then we have number 10, which is the chain rule. So we could just repeat the process. Right? This process is repeatable. So I really don't have to show you 4 and 5 and 6. I just show you 2 and 3. And then you can extend the pattern as many times as necessary. So you take the derivative of the outside function. That's f. You don't mess with the inside. So you leave g and h alone. Leave them, they're protected. Then you go to the next function, g. You take its derivative. But h is now protected, so you leave h alone. And then finally you go to the last function, which is the h. It's like those stacking eggs or the Russian stacking dolls, which used to be very popular. I don't know how popular they are in 2024, but nonetheless, there's one inside of another, inside of another. And so this process would continue for any countable number of functions. You can just continue to differentiate all the way until you get to that little baby egg in the very center of all the nested eggs or dolls or whatever they are. So let's do an example. Example 8. Y is ln of x squared plus 6x minus 9 to the 5th power. All right. So again, this is the first time I've done a triple, so I'm just going to identify h is the innermost function. That's h. I'm using shorthand and just saying h. Right. Then g is the next one, blank to the 5th. That's your g. And remember, h goes inside of g. And then f is the ln of blank, and all of this goes inside of f. So it's like there's one inside of another, and there's 3 layers to this mathematical onion here. Now again, you don't have to actually write that down. This is just sort of, I call this bookkeeping, just kind of keeping track of what order everybody is in. So the derivative, also known as y prime, that's another way to say dy dx, or f prime, same thing. Remember, y is the same as f of x. So let's do it. ln, it's right back to earlier in the video when ln is one of those really nice ones. It's 1 over blank, and then you copy everything exactly the same. Don't change any of the terms. It's this whole function put right into the denominator right here. All right, so that's your f prime. So this represents all of this right here. That's this one right here. Now we go to the next one. All right, that's going to go right here. Put a little dot right here to multiply. All right, g prime. So now we're at g. So g is blank to the 5th power. So we're going to put the 5 down in front and raise it to the 4th. And then all of this goes inside of there. X squared minus 6x plus 9. And then finally, my h of x, that's this one right here. That's going to go here. I need that space, sorry. That's probably the easiest one. The derivative of h, it's the easiest one to calculate. It's going to be 2x plus 6. And just to be safe, I'm going to put some parentheses around it. Now, you could just leave it messy like this. All right, you don't want the boxes and circles and triangles. But I'm going to clean it up a little bit. I've got x squared minus 6x to the fourth and x squared minus 6x minus 9 to the fifth. These are the same factors. Oh, shit. I got the signs backwards. This one's plus, and this one's minus. I got to make sure the signs match. I'm glad I caught that now. All right, cool. So they match. I'm actually glad I screwed up. So they match. If they don't match, then something went wrong. So now I can combine them. I can cancel all four of these guys. Those are all gone. And then there's only going to be one of these left. So my denominator is just x squared plus 6x minus 9. I don't even need parentheses anymore because there's only one factor left. If you want to put the parentheses, it's okay, but they don't do anything. Unless there's a number greater than 1, then they don't really do anything. All right, now this is 1 times, so this dot, I actually recommend bringing the dot up, multiplying across the top. 1 times 5 times 2x plus 6. It's going to be 10x plus 30. And that's your final answer. 1 times 5 times 2 is 10. 1 times 5 times 6 is 30. And the sign is plus. So that's your final answer. Probably shouldn't have boxed that. That's just showing you one piece of the answer. This is the final answer. Not too bad, huh? Again, someday, a couple weeks, we'll see how you can actually do something with this result. Right? This whole homework for this section, chain rule part 1, is just exercising the principle. We're not really doing anything with our answer. I might do one tangent line problem in a minute. We're almost there. We're almost done. Hang in there. I'm tired too. It's been a long day. I normally film these videos before lunch in the morning. I do all my online in the morning, and then I have other responsibilities in the afternoon. But today I had a free afternoon, so here I am. If you're watching this on YouTube, this is hot off the press, just recorded this afternoon. You don't know what day of the week it is, but I could say it, but it wouldn't matter by the time you watched it. All right, example 9. So y equals, let's do another triple one. E to the log base 8. Oh, God, that's not one of the nice ones. Oh, sorry, it's not E. Oh, man, this is even worse. I was looking at the wrong problem. It's 5. Oh, God. I just made up a terrible problem, but it's good. We're almost done, so we can suffer right together at the very end. All right, and then 2x to the 4th. This is about as bad as it gets. So find dy dx. All right, the first thing we're going to have to do is remember the derivatives of non-natural exponentials. The derivative of 5 to the x is 1 over x ln of 5. Now, I screw this up a lot. I think I've even screwed it up. I hope not in one of my videos, but who knows? I don't know. If you've caught me slipping. Occasionally, I'll write log 5. I have unresolved issues from 30 years ago when I was in college. I had a professor who wrote log, but they actually meant natural log, but they just said, hey, I write log when I really mean ln. And they told the whole class that we just have to get used to it. And so we got used to it. And I got used to it. I wrote it, for an entire year. I had the same professor twice, 2 semesters in a row. And so I just got used to writing log when I actually meant ln. And then when I became a professor, I tried to be very distinct about whether or not I meant log or whether or not I meant ln. They're different. The original function might be a log, but this is an ln, okay? And then the derivative of a log. Oh, see, I got these backwards. See, I knew I was going to screw this up. This is 5 to the x. It is nice to write them next to each other. It keeps you from screwing them up. So this one is 5 to the x ln of 5. This one is the 1 over x. And I'm going to blame it on my college professor from Berkeley from, the 1990s. So a little bit of recall before you do the problem will go a long way, even for an old professor or middle-aged professor like me, to make sure that I don't get these screwed up. Right. The ln's and the e's are easy. They're easy, natural and easy. These ones are very unnatural, and you have to really make sure that you're writing them down correctly. So I got them right this time. Derivative of 5 to the x is 5 to the x times ln of 5. Derivative of log 8x is 1 over x ln of 8. All right, so now we're ready to go. Ready? I'm going to need more space. dy dx. dy dx. All right, so first we follow this rule. That's going to be 5 log 8 2x to the 4th times. Now we follow this rule. 1 over 2x to the 4th times ln of 8 times, I don't need a rule for 2x to the 4th. I mean, you know there's a rule. It's one of the very easy rules. It's called the power rule. The 4 times 2 becomes 8x, and the power becomes 1 less, which is 3. All right, that's probably the easiest of all the steps. Doesn't require much prior knowledge. So that's your answer. If you get this far in the homework and you want to type it in like this and see if it marks it right, go right ahead. I'm going to do a little bit just because I think I can. I think I forgot something. Oh, I did forget something. 5 log 8 2x to the 4th times ln of 5. I almost forgot this, even though I wrote it down. I'm glad I stopped and took a breath before I forgot that. I remembered it down here because I made such a big deal about it, but I almost forgot it up here. All right, now we're ready to simplify. So what do we got? Let's do the best we can. We got 8 divided by 2 is 4. That'll be nice. We got x cubed and x to the 4th, so that's going to be x to the 1st. Right. Now here's a trick you might not remember from basic algebra. ln of A over ln of B is log base B of A. Algebra fact. You could call it a fun fact if you think it's fun. It's an algebra fact from logarithms. It's what's called the property of logarithms. It's also known the change of base formula. So I'm changing from a base of natural log into a base of B. So my B is 8. So this is 5 log base 8 of 2x to the 4th times log base 8 of 5 times 4. Don't forget that 4 squeezed in there, all over x. I probably would get rid of this dot and just put the 4 right here. And then I only have to have one dot. And if you want to have 2 multiplication dots, you can. You don't actually need a dot. But as long as it's clear that these are being multiplied, you don't need a dot. You could also put an extra set of parentheses, whatever you want to do. You could have just stopped a few minutes ago and said, I'm done. I always like to try to simplify it as much as I possibly can, especially because I know where we're going with this. And the simpler we make it, the easier our life is going to be when we get there. Well, I've only got time for one more, and it's going to be sort of a revisiting of the original concept of a derivative. I don't ever want to forget where we came from. Remember where we came from? Instantaneous rate of change. Find the equation of the tangent line to the graph of the function f of x equals ln square root 7 minus x. This is like our roots. This is our mathematical roots, where we came from. Tangent lines, instantaneous rates of change, slope of the tangent line at a point. Okay. The first thing I would do before I even do any calculus is plug this number in to find the y value. You're going to need it later, and we might as well just do it now. So f of 6 is ln of square root 7 minus 6, which is ln square root of 1, ln of 1. Another fun fact, the log of 1 is 0. All right, so we're going to save this. X is equal to 6 and y is equal to 0. We'll come back to that later. If it's been a while since you did algebra, you could just put that in your calculator, ln of 1, and it'll tell you it's 0. The reason why it's 0 is because e to the 0 is 1. This is the reason why. Anytime you do a logarithm, it's the inverse of an exponential. So you're saying, well, if ln of 1 is 0, well, that means that e of 0 is 1. It's just inverting the operation or the function. But I'm not doing that today. We're doing calculus today. So now let's do the derivative, f prime of x. All right, this is the chain rule all day long. All right, this is one of the easier ones, ln. It turns out that ln is very common in this course, so we might as well hit it as many times as we can. So it's going to be 1 over the square root of 7 minus x. That's the first chain, first link. That's your f. That's your outer. Times the second link, square root. So that's 1/2 7 minus x to the negative 1/2. All right, we did that at the very beginning of this video. A square root is the same as 1/2. And then you subtract 1, so it becomes negative 1/2. And then finally, the little baby, at the center of the dolls, that's the inside, 7 minus x. The derivative of that is just negative 1. Yeah, there's an invisible negative 1 right in front of that x right there. It's the slope of the inside function. All right. The only thing here that belongs in the top are the 1s. 1 times 1 times negative 1. So the top is just negative 1. This 2 belongs out in front. None of these numbers are even, so I can't divide them by 2. If I had an even number in the numerator, I would probably divide it by 2 to get rid of that 2. But that's what it looks like when you don't get rid of it. Then you have the square root of 7 minus x, and then you have another square root of 7 minus x. In other words, you have the square root of 7 minus x squared. Squared. You have 2 of them. And so those are going to cancel, the square and the square root. And so your final derivative is negative 1 over 2 times 7 minus x. If you want to simplify it, you can simplify it 14 minus 2x. So that's your derivative. All right, and so now to find the slope, plug in whatever is given to us. So I saved that 6. So I've got negative 1 over 14 minus 2 times 6, 14 minus 12, negative 1/2 is going to be my slope. Now I need to find b. Remember, your equation is y equals mx plus b. All right, I've got y, I've got m, and I've got x. So we'll put 0 for y. We'll put negative 1/2 for m. And we'll put 6 for x. And so b is positive 3. So my answer, y equals m, there's my slope, times x, plus my b is 3. And that'll do it for today. If you're curious what this looks like, I've got about 2 minutes left. Are you curious? You're going to have to do it in chapter 3 anyway. I'm going to have to buy another one of these when we get to chapter 3 because this one's going to be worn out by then. So we have the point 1, 2, 3, 4, 5, 6, and 0. There's a dot right there. This graph has an asymptote at 7. And then the tangent line looks like this, negative 1/2 x plus 3. So it crosses right here at 3. So that's what the tangent line looks like. That's the tangent line, this blue line here. And then at 6, the graph goes like this. And I don't know. We would need more information to see what the graph looks like. And that's going to be done in chapter 3. Coming soon. For today, all we know is the tangent line and one dot I did know that there's an asymptote because it had the 7 minus x. So that tells me that the graph must be less than 7, the domain, which we did talk about in this chapter. We don't have enough information yet to draw the rest of the graph, so I really can't commit to what's going on here. I do know there's an asymptote and a point and a line. That's all I know. If I wanted to know more information, I have to come back and see the rest of the videos. But until that day comes, do your homework. We're almost done with chapter 2. So I'll be talking test preparation soon. Until next time, I'm Dr. Jordan, and I'll see you on the internet.